Thank you very much. The speaker is not here, but I think that talk gave some nice intuitions to the rather technical paper. So this was very nice. We cannot ask questions now. That's a pity. But as the technical issues used up all our question time, we are actually pretty happy that we can move to the next talk just in time. And Matias, I would ask you to share your screen, please, if that is possible.
Yes.
Great, I can also hear you. So all the preconditions for nice talk are there. Yeah, so the next talk we will hear is given by Matias Scharager. And if I understood it correctly, you're a first-year PhD student at Carnegie Mellon University and just received your bachelor this year. Is this correct?
Yes.
Probably our youngest speaker from a scientific point of view, and congratulations for getting a paper to formal method this young in your scientific career. Yeah, and I'm looking forward to your talk. So please, the stage is yours.
Thank you. Well, hello, everyone. I'm Matias Scharager, and this is a joint work with my collaborators, Katherine Cordwell, Stefan Mitsch, and André Platzer. Katherine and André are also on this talk, so they can help answer questions. Additionally, I'd like to thank Fabian Ilmer, who also contributed to this project, but wasn't able to be a co-author due to his employment restrictions. So to start off, let's consider this problem shown on the slide, where we determine if there will be a car crash. Although this specific problem is about car crashes, it is easy to see how various other problems can be modeled in a similar way. First, there are a lot of unknown variables that go into modeling this problem, such as the time and the speed of each car. The x and y coordinates of each car can be expressed as multivariate polynomials in terms of all of these unknown variables. Finally, the question we want to analyze is the sentence at the end, there never exists a time t when two cars have the same x and y coordinates. What makes this difficult to analyze is this notion of never exists, which uses an existential quantifier on a variable that ranges over the real numbers. It's not enough to analyze just a few points of time. Instead, we need to consider all possible times to ensure that we have everything covered. The way we handle these quantified formulas is through a process called quantifier elimination. Notice that the red formula and the blue formula are both equivalent to true, but it is far easier to see for the blue formula than the red formula. Somehow we need to take this red formula and transform it into an equivalent blue formula that is quantifier free, while preserving logical equivalence with the original formula. The first example is relatively simple. However, this next red formula is already slightly more complicated because it involves these free variables x and w. And so we get the result of this QE is this blue formula involving x and w. In general, QE problems can get extremely complicated. And miraculously, the Tarski-Steinberg theorem tells us that in the first order logic of real arithmetic, there are algorithms that can convert from any formula into one with no quantifiers. Here, the first order logic of real arithmetic just means the kind of formulas we have written on this slide, where we have polynomials with real valued variables and rational coefficients. The fact that we can do this transformation is incredible, because now we would like to write algorithms that perform QE. There are two things we want out of our QE algorithms, correctness and efficiency. Most importantly, we want our algorithms to be correct, which means they preserve the formula equivalence after converting to quantifier-free form. To ensure this, we would ideally like to verify algorithms in a theorem prover. This lets us trust that the algorithm will always produce an equivalent formula as it is verified up to the theorem prover's trusted core. Moreover, we want our algorithms to be efficient. This means we want them to run fast and result in a small formula. The most efficient known algorithm for quantifier elimination is cylindrical algebraic decomposition, or CAD. And this is still doubly exponential in the worst case. So quantifier elimination is indeed a hard problem. The big issue is that it's very difficult to have both efficiency and correctness. This often leads to sacrificing one for the sake of the other. So in practice, the QE questions are often handled with these black box solvers, where we sacrifice formally verified correctness in favor of efficiency. For example, the theorem prover Chimera X outsources these QE queries to Mathematica and Z3. this introduces an unverified hole in an otherwise fully verified proof. It would be great if these black box algorithms were entirely bug-free, but we can't guarantee that correctness without proving it in a theorem prover. So how much can we actually trust these black box tools? To find out, we ran these 378 benchmarks from the literature on various existing tools, Mathematica, Z3, SMT-RAT, and RedLog. For these tests, we took a decision problem A and its negation not A, and we ran both on all of the tools. The red marks you see on the chart represent the cases where the tool was self-contradictory, meaning that it stated both A and not A were true, which is impossible. In total, there were 137 of these contradictions. We reached out to the developers of these tools and learned that the mode of SMT-RAT that had inconsistencies does not actually support quantified formulas, but only quantifier-free formulas. So according to the developers, their parser was silently ignoring quantifiers in the inputs, which meant that the output was only correct for existentially quantified formulas. In RedLog, there were several errors, which date back several years, at least to early 2018. Although we didn't find errors in Mathematica and Z3 in these experiments, that doesn't mean that there aren't any errors, as these are very limited benchmarks that we'll pull from the literature. Other recent works using fuzzing found some errors in Z3, and André Platzer's lab group has a history of finding bugs here and there in Mathematica. This is not to say that these tools are bad, but it does show how easy it is to create bugs in this real arithmetic setting. So to remove these bugs, we must verify these algorithms in a theorem prover. This might require making some small sacrifices in runtime efficiency, but given the safety critical nature of the applications in which QE problems arise, losing some amount of efficiency to gain correctness is a reasonable trade-off. There have been a few efforts improving QE algorithms in the past listed here. There are two general purpose QE algorithms that have been verified. Both have non-elementary complexity, which means that the runtime cannot be bounded by any towers of powers of 2, which makes them impractical. Additionally, the univariate case of CAD has been verified, but no one has yet managed to verify the full CAD algorithm for multivariate polynomials. So we would like to find a QE algorithm that is reasonable to formally verify and is fast enough to use in practice for solving these QE problems. The virtual substitution algorithm, or VS, is a very efficient algorithm for solving quantified formulas with low degree polynomials, which makes it a great candidate to formally verify. There are two different flavors of VS. The equality VS targets low degree equalities in formulas, while general VS additionally deals with low degree inequalities. There have been some previous works on formally verifying virtual substitution. Tobias and Nipkow formalized linear virtual substitution in the theorem prover Isabel Hole, and one of his students, Amin Shaib, verified quadratic equality virtual substitution. Our work is the first to tackle quadratic inequality case, in contrast to previous work, and our approach is explicitly designed with practicality in mind, so there is no overlap. So in our work, we formalize algorithms to perform equality VS and general VS for both linear and quadratic polynomials in the Isabel Hole theorem prover. In total, our formalization is around 23,000 lines of code, and it's available in the archive of formal proofs. To get an understanding of how virtual substitution actually works, let's quickly run through this example of equality VS for solving this problem. First, we identify that the y squared x squared equals 2 is an equality atom with the quadratic degree in x. And using this, if we solve for x, we get that it is either the positive or negative square root of 2 divided by y squared. And we need the additional condition that y cannot be 0 to ensure that we're not dividing by 0. So these are the only two possible values that x can take. We can plug in these values everywhere into the formula to get this equivalent formula without quantifiers. However, we're not done here because we're no longer in a well-formed formula for first order logic of real arithmetic, because we can't have fractions or square root in the formulas. As such, we need to multiply out our fractions and sometimes square both sides to get rid of the square roots, and to result in a logically equivalent formula that's to the original formula, but without the fractions or square roots. And so we get this final formula here. This is a very simplified example for the purpose of presentation, but even in this simple example, one can imagine how easy it is to forget a condition, such as the y not equal to 0 part in the final formula, which would break the equivalence guarantees we want in a QE algorithm. If we want to think of the general case with low degree inequalities, the problem becomes much harder. In equality VS, we can virtually substitute the roots of a low degree equality, but it's a lot less clear what we want to virtually substitute for the inequalities. For example, it's not clear which values of x we should plug in into the formula at the top. What we'd like is a way to substitute infinitely many solutions of the inequality instead of single values. But this is not immediately clear how we might do this. However, if we look at the roots of the polynomials, we know that the sign value in between two adjacent roots does not change because polynomials are continuous. This means we can use the roots as a way of discretizing the possible ranges. This leaves us with the virtual substitution idea of substituting off roots, or r plus epsilon, where r is the root of the polynomial and epsilon is an arbitrarily small positive value that can grow and shrink to fit inside the ranges between the roots. This accounts for all the ranges to the right of the roots, but not the range to the left, so we need an additional value of -infinity to account for the leftmost range. And we can see in this picture, the polynomials from the expression are plotted along with the off roots and the -infinity that virtual substitution will substitute. These values of plus epsilon and -infinity exist in the extended reals and non-standard analysis, but are not part of the reals. So virtual substitution uses them to ensure that the algorithm generalizes to arbitrary examples, which can have many different configurations of roots on the number line. And we need to do algebraic manipulations to remove the, like in the same way that we remove the square roots in the fractions, we must virtually substitute epsilon and -infinity to prove that the resulting formula captures the logical meaning while staying in the first order logic of real arithmetic. We can see how much harder the general case of VS is compared to the equality case. In the equality case, we can inspect every polynomial separately, so there are nice induction principles that finish the proof. But in the general case, we need to be considering all possible ranges from the start, so we can't prove it via simple induction. Now I'd like to point a few particular significant implementation details. There's a lot more details regarding the formalization that are explained thoroughly in the proceedings. In this first box, we use a clever trick to transform many difficult soundness proofs involving multivariate polynomials into analogous proofs involving univariate polynomials. The trick is that the correctness of virtual substitution can be proved per valuation. So we can often pretend that real numbers have been plugged in for all but the variable of interest. Then we can lift these proofs to the multivariate framework. And this is very nice because it's a lot easier to work with these univariate polynomials in Isabelle whole than it is to work with multivariate polynomials. Additionally, in the bottom left of the slide, we see this block of quantifiers in our formula, and we can choose which quantifier to eliminate first. This allows us to run an arbitrary variable ordering heuristic on the formula F. Since these heuristics are known to be of practical significance for QE, this is a significant feature of our framework. And our formally verified framework is also fully modular. We can take any arbitrary optimization, heuristic, and QE algorithms and prove properties of each of these separately, and then combine them in our framework to get the whole verified QE algorithm. And also looking at this last box at the bottom right, since we only verified virtual substitution up to quadratic polynomials, but we want to have a general algorithm for QE, our algorithm must account for the possibility of failure while continuing to eliminate the rest of the quantifiers. As such, we devised special algorithms to squeeze out as much information as possible from underneath quantifiers, increasing the number of atoms that VS algorithms can utilize and allowing us to simplify the formula as much as possible. So now let's talk about our experiments. To test the efficiency of our algorithms, we used the automatic code generator functionality of Isabelle to export our code to standard ML and test it on the benchmarks from the literature. So if you remember this plot from earlier, it is now expanded to include all algorithm at the end called LEG. And exporting our code does require trusting Isabelle's code generator, but this is not unreasonable because verifying an algorithm and exporting it is significantly more trustworthy than just writing an algorithm. And there is independent work towards verifying Isabelle Hole's code generator. And we can see that our algorithm solves quite a lot of test cases. To be more precise, we solved 304 out of the 378 test cases, which shows it's a very effective method for solving these QE queries. Here are some efficiency plots to see how long it takes to run these tests. The graph shows cumulative timing information for two different sets of benchmarks from the literature. And our algorithms are the ones in blue that are being pointed at by the arrows. And in these graphs, the flatter the curve and the more tests solved, the better. We're outperformed by existing tools, but these results are still along the lines of what we've hoped for. We never expected to outperform these tools, some of which have been optimized for decades. And all algorithms solve quite a few examples and have the added benefit of being fully verified. Given the safety critical nature of applications in which QE questions arise, we are okay with giving up a little bit of efficiency in favor of correctness. So in conclusion, we verified linear and quadratic virtual substitution in Isabelle Hole, and our virtual substitution formalization is both correct and demonstrates promising efficiency on benchmarks from the literature. This work takes us closer to bridging the gap between verification and efficiency, showing that we don't always need to sacrifice one for the other. So thank you, everyone. Are there any questions?
Thank you very much for this very nice talk and also for the nice work you've done, obviously. Are there any questions? You can either post them in the chat. Yes, Jonathan, please.
Hi, Matias. Thank you very much for your talk. It's very interesting, your work. I just want to know if you already know of the missing cases, what were the difficulties there? Can you expand a bit on that?
Yes, so because we're doing this virtual substitution, every time we do the stepping of plugging in, we run the risk of our polynomials increasing in complexity. So it's like no longer quadratic. And so for these complicated ones, it involved like multiple stages of virtual substitution. And in those multiple stages, we left the quadratic polynomials. There's also like sometimes the way that we did the substitution was like it expanded the formula so much that we could not finish solving this algorithm. But if we had run it for longer, then it probably would have.
Thank you very much. I look forward to hearing more about your work in the future.
Thank you.
Thank you very much. Are there further questions from the audience? Well, I'm usually working, I'm usually using formal methods and not developing formal methods myself. So this might be an easy question, but I wondered, you first did this whole substitution for equalities and then later also for inequalities. And your motivating example was that you check whether some robot or vehicle is at the same coordinate. So with the general inequality framework, can you then also solve this for similar coordinates, not only for the same coordinates?
Well, we have inequalities, and so like that's less than and not equal to, and also less than or equal to. So all of those add like more expressive power for like solving extra formulas. So yeah, if you have any problem that can be expressed in that way, then if everything remains in the quadratic degree, then we can solve it using this algorithm.
And did you have such more complicated problems in your benchmarks?
Yeah, the benchmarks are they model like different physics equations or like other problems that you can see from the real world. So they are sufficiently interesting problems that we did solve. But you can continue adding more, like this is a limited set of benchmarks. There are lots of problems that fit in this category.
Okay, and can you see it in the benchmarks when you move from the equalities to the inequalities? Does that also mean that you have more to sacrifice more efficiency?
Yes, so because of the fact that the general one does this plugging for all the ranges, there's more steps involved. Specifically, our LEG algorithm starts by looking at like lucky cases of like constant coefficients, then goes into the equality case, then goes into the general case. And so doing it in that order helped us get the best results because we're going like increasing difficulty. And so yeah, but the equality case has like a lot of added benefits as well because it has the induction properties. So you can just look at any one of the equalities and substitute it in.
Okay, thank you very much. Yeah, if there are no more questions, thanks again to the speaker. I hope you will also be available at one or the other coffee break.